So the next presenter is my previous colleague, and still my colleague, Dr. Ylias Sabri, who I worked a lot during the time in RMIT. Dr. Sabri is a senior lecturer in environmental and chemical engineering discipline in RMIT University. He manages the Nanotechnology and Chemical Sensor group in RMIT University. His research focuses on the chemical sensing, material science, mercury monitoring, catalysis and removal, nanomaterials, solid-state transducers.
All right, thanks, Ahmed, for that introduction. Before I start, I must declare that the work that's being presented here is teamwork with myself, Ahmed Kanjani there, the chair in front of you, and Dr. Samuel Ipililo, who is one of the guys in the audience. So the outline of my presentation, I'm going to be talking about reproducible surfaces and repeatability of chemical sensors. And the way I'll present this, our approach has been to develop colloidal crystal-based sensors, and this includes optical sensors, electrochemical sensors, and also gas sensors where we've actually deposited colloidal crystals on QCMs, SAW, and resistive transducers. Before I start, for those students out there, I just wanted to put this slide up. The three terms that we use in terms of sensor performance is accuracy first. So accuracy is a measure of the degree to which a given output conforms to an agreed upon standard. So when you're validating your instruments, okay, you have to make sure that it's validated against accepted sensor output. And then you got repeatability, which is the ability to obtain the same result when you're measuring a quantity over and over again. But when it comes to reproducibility, you want to be able to measure the same output when you measure something under different conditions. So I've put those three figures there for you, the three different type of sensors. The first one is a highly accurate, highly repeatable sensor where you're actually hitting the target at the validation point and you're getting that repeatably. And then you have a sensor that is low accuracy but high repeatability, so you're not hitting the target, you're not getting the right answer, for example, or output, but you're getting it repeatably. And then you got a really bad sensor where you have a low accuracy and low repeatability, so nothing is really working out there. Now, when it comes to reproducibility, you need to be able to control both your fabrication of the sensor, as has been mentioned many times before here in this conference, reproducibility of your materials, and also the conditions that you'll be testing on. So you got to be able to reproduce all that. What I'm going to talk about today is the work that we've done in terms of trying to reproduce our materials, okay, the material part. We've done a lot of fabrication of the sensors, so we're looking at materials. The way we do that is we use templating using colloidal lithography. There's many methods to do this. We're doing colloidal lithography. And then to do colloidal lithography, there are many methods, but this method especially we've made it so we don't have to use a Langmuir blowjet, where you'd get a better surfaces. But in order to get going, we've developed this simple method, or we're using the simple method to actually achieve our colloidal crystals. So how we do that? We use the air-water interface by depositing our colloids on top of the water surface. And in order to bring them into a compact form, we use a surfactant, depending on the surface charge of your colloids, and that brings it all together. As you can see on the figure above, this guy has actually put his finger in soap beforehand, so he's got surfactant on his finger, and he puts it into the water, and all the colloids or particles on the air-water interface gets compacted together. In a similar fashion, we've done that over here. We then go and put our transducer into that solution and pick up that monolayer surface, and we end up with a transducer that has the monolayer of our template polymer or colloidal structure. We can repeat this if we like and get multi-layers, but in this talk, we're not going to be presenting that. We're just going to be looking at our monolayers, okay? So the type of, the reason we do this is because we want to get long range ordered crystals. Okay, we want to get the same kind of structure all over the surface over a long range. So you can see close up, we get these colloidal structures, and the images before were from a zoomed out image. So you can see over a large surface, you get the same structure all over. Of course, this is colloidal crystals is what it's all about. Now you can try to get different types of structures depending on the lithography that you do. So you can get honeycomb structures, or you can get this honeycomb star structures. And this is very simple. These two surfaces, all we've done is change the way we deposit our material onto our template. So in the top case, you see that we had our polystyrene structure on top of a zinc oxide film. And all we did was we did E-beam evaporation of our silver. And then when we removed our polystyrene template, we ended up with these star structures. In the bottom case, we did just the deposition of our material differently. So the zinc oxide sol gel was spin coated, and then we removed our polystyrene template, and we ended up with this honeycomb structure of zinc oxide. Okay, so there's a lot that you can do with colloidal lithography, and that's why we want to implement it in our sensing systems. Another device that I'll be talking about a lot in this talk is a quartz crystal microbalance. So just quickly, it's a gravimetric sensor. It's mass-based sensor, so the output is directly related to the mass that gets deposited on the surface. So if you have a gas and you got a surface, you get your molecules deposited on it, you get a response, and then when you regenerate your sensor, that response comes back to baseline. If you modify your surface, you could improve your surface, your sensor performance, for example, response in this case. So now we got all that out the way. Now we can start doing colloidal lithography and get reproducible surfaces. You can see here we got a QCM that's got titanium electrodes. In this case, we put polystyrene polymers on it, and all we do is we deposit gold and silver on top, and we get our colloidal crystals with two different materials. Now, what we did with this is we can compare this with a gold control, a thin film, which is in the bottom right corner of the screen, which you can see. So that's what the structure looks like if it's a thin film, but on the colloidal surfaces, it looks a little different structure. And we've gone and looked at the property of this, such as the surface area, how much that's increased. The way we did that was use the RAND method, which means dipping our gold materials into sulfuric acid and try to oxidize the gold surface, and then they count the charge on that and compare. It's called the electrochemical surface area. Compared to a thin film of gold, our electrochemical surface area of this colloidal gold structure is about around 4 times higher. So 4 is the magic word to remember when I show you the next graph. What you see here is the response towards mercury. I'm sensing mercury because mercury is a poisonous gas. I don't need to go into that, but it's a vapor mercury, okay, elemental mercury gas. We're exposing them to gold because they have high affinity to each other, and we're seeing the response enhancement. So if you look at the graph on the right where we've done the analysis, you can see that the gold control has been normalized to 1 in terms of the response, okay? And then when you look at the gold sphere, here it's got 16 times enhancement in terms of response magnitude. Remember the magic number 4, we're getting 16 here. So what we find here is that the increased response is not just due to surface area. There's other chemistry that's involved when you're talking about gold and mercury interaction. There's diffusion that occurs and amalgamation. So it all makes sense, and I won't go too deep into that. It's not the topic. What we find is that using these colloidal structures, we have increased our accuracy, our response rate, and our repeatability of our sensors. So by using a combination of reproducible materials and the way we use the system to control the temperature and the pressure, we're able to get repeatability and accuracy for our sensors. What else do we find from here is that the silver surface has completely deteriorated over time with mercury amalgamation. This is normal for silver. However, gold has withstand its morphology even after the long-term tests. So from here, we've told we're going to avoid the long-range order structures for silver. We're just going to concentrate on gold and try to improve that and make more reproducible sensors. Now, how can we enhance our sensor performance? We've had a material before that you may have heard about before. We've patented and it's been on the news. It's gone to pilot plant trials with the mercury sensing. That's the one on the left. We call them nanospikes. And the one on the right, I just showed you guys just before the performance. So what we thought was, let's combine these two, but still be able to make reproducible surfaces. How do we do that? Again, we do the same process. We take our QCM, we put our polystyrene colloids on it, we deposit gold, but this time one extra step, we electrodeposit those structures that I showed you, the nanospikes, onto these colloids, and what we get is this nano-urchin type structure. So if you see on the right, what we have is the polystyrene and then the gold and the spikes deposited on top of it. And we've deposited these spikes at different deposition times, and that's why you see the different SEMs with different size spikes. Now, it's still an ordered structure of a long range. If you look at the bottom right corner of your screen, you got the fast Fourier transform image, which shows a hexagonal packed, still long range ordered crystal. And this allows us to actually control the size of our urchin-like structures. So in terms of sensor response, now if you look at the top right-hand corner of the screen, you got the gold control on the left in terms of surface area. Okay, so we're getting increased surface area as we're increasing our electrodeposition time. Those are the numbers you see: 6 minutes, 8 minutes, 10 minutes, and so on. And then you got the response enhancement on the bottom right-hand corner, and you can see we got up to 25 times higher response. QCM has its limit, so there's a certain limit of mass you can deposit on it, but on other type of sensors you could probably go even higher. Okay. The other interesting thing about the structures is also you see that they deposit straight on top of the tips, and we'll have a look at that a bit later where we've done some modeling. In terms of sensor performance, we see that at 75 degrees we get really low LODs, limit of detection. Our reproducibility is really high. We got good accuracy, but more importantly, we got a reproducible material that we could deposit on QCMs and get the same similar response. Okay, so we thought, okay, one of the biggest issues that we have is we've published some papers on galvanic replacement reaction. Galvanic replacement reaction is basically dipping a less noble metal into a more noble metal solution and then getting it to galvanic replace. So in this case, for example, on the bottom left-hand corner, you got a silver particle. If you dip that into a gold solution, your gold chloride will come and reduce as gold particle on the surface, whereas your silver will galvanic replace and go into solution, oxidize into silver aqueous solution. Okay, so we've done this with a gold palladium system, which you see on the top left-hand corner on a thin film. There's no colloids here, no colloidal structure, and you see that the particles grow anyway. Okay, as we increase the time of reaction, it's arbitrary growth. Same thing on the right. We've done this with nickel gold. So you got a nickel substrate on the top left side at 0 hours. And then as we increase the reaction time inside of a gold solution, again, we see island growths, but they just grow anyway that they prefer. How can we control that? We've done this now on a colloidal structure. What you see now is that we can actually get a more uniform structure over the surface. So on top of each colloid, each one is now acting as a reactor system. So all these particles are growing equally onto each of the colloidal particles, right? So from the close range, you could still say that it's not uniform, as Antonio Charcoli was talking about before with his structures. That's true. So at close up, it might look a little bit disordered, but when you look at it at a large, long range image, then you'll find that it's an ordered structure. So you're still getting a reproducible surface. So let's put this into real application again onto a sensor. We put our colloids again. This time we put our palladium deposition, dip it into a gold to do our galvanic replacement, and we do this at different times of gold deposition to get our different amounts of gold on the surface, so we can get a good control of the amount of gold that we can use on the surface and still get our ordered structure, and then use that for sensing. In this case, we've exposed it to mercury again. Palladium is not as selective to mercury as gold, so that's why we did see a bit of issues with selectivity. However, the concept of trying to get reproducible surfaces with galvanic replacement, which is otherwise impossible or less likely, we're still able to get that. We've tried a different system, gold nickel. to see to undergo glucose sensing. The reason we've used gold and nickel is because they overlap at the same voltage when you're trying to do chronoamperometric glucose sensing for diabetic applications. Okay, so we've got a nickel substrate colloidal structure, and we've galvanic replaced gold on that. So now you got gold and nickel playing together to synergetically to try to detect glucose, and we're able to detect glucose from 20 micromolar all the way up to 10 millimolar. And we've done some selectivity experiments regarding physiological related contaminants, and we got quite good results with the other contaminants except for uric acid and acetic acid. So moving away from mercury in gas, we went, and the biggest issue is now being able to detect mercury in water as well. So we're trying to detect very low concentration of mercury in water. So could we use our reproducible surfaces for detecting liquid-based pollutants? In this case, what we did with our Indian collaborator, we got them to design our organic ligand, okay, which had these amine groups that are attracted to both gold and mercury. We deposited them onto our colloidal crystal. So you can see on the bottom right corner there in the schematic, once you place these organic materials on your colloids, you try to do Raman detection, you get a low Raman signal. However, once you introduce mercury, because of these amine groups and interaction of the molecules with each other, you get enhancement in the SIRS response. So this allowed us to detect very low concentration of mercury because it actually does the enhancement of Raman. So you can see the lowest concentration that we put in around the 1400 centimeter. We could see that the signal is increasing even with 1 femtomolar of mercury. So at the time when we published this paper, this was the lowest detection limit ever reported. We were looking at attomolar of mercury detection, and the selectivity was quite good as well. And selectivity, of course, came from the molecule that we had designed, but sensitivity came from the reproducible surfaces that we had developed. So we thought, what else can we do to improve our sensing understanding? So this time we're not just depositing our colloidal particles onto the surface and depositing other materials, but we're actually doing a middle step, which is we can see the second step here is called plasma etching. So we're actually reducing the size of our polystyrene once we deposit it on the surface using plasma, and what this does is it changes the size of our colloids uniformly, as well as the spacing between them. Then we went and deposit our gold in this case, and then we remove our template, our polystyrene template. And what we end up with, as you can see on the SCMs on the left side, the left panel shows you before removing polystyrene, and the right panel shows you the structure after removing the polystyrene. So you can see that the gold triangles in a honeycomb shape on the right, that's from the no etching at all, no plasma etching. And as we increase the plasma etching, you can see that the pore size decreases all the way down to D2, where we've etched it and got the smallest pore size for that application. Of course, we did gas sensing with this, and from our data, we could see that as you reduce the polystyrene size, your sensor response to mercury increases. Why? Because you got more gold, you got more sensitive layer on the surface. So that just makes sense. But to go and look at this more closely and analyze it, what we find, so if you look at the graph on the bottom right, the two graphs, B and C, what you see on the graph is that as you increase your etch time, so both x-axis has the etch time, as you increase your etch time, you're increasing your gold surface area, of course, because you're depositing more gold. And the one on the very left side is gold control. Okay, so you're decreasing your gold surface area in the first instance where you have no etching, and as you increase your etching, you're getting back close to your gold control surface, of course. On the right side, we see the same thing with the gold mass. Okay, the mass of the gold control is, of course, the highest. Once you do the etching, you're depositing less gold. Of course, those triangles have less gold, and as you're increasing the etching time, your gold mass increases again. But now the interesting thing is the response. Your gold control has a certain response. 8 picogram of mass has been deposited on this QCM. But then as you etch it with 0 minutes, you get a lower response, and then the rest is comparable again to the gold control. And even though for the last etching time, we have less gold than the control gold, but our response is higher. How can you have this? So you got less sensitive area, but more response. So the only thing we could attribute it there from our characterization was to say there's the defects that we've created at those edges. And of course, mercury interacts with the defect areas of gold more than any your plane surface. So it likes more crystal defects. And so we learned something from here. So we saw another system that does this is galvanic replacement. So can we actually show this with galvanic replacement reaction and see that it actually grows on the edges? And that's exactly what it did. So when we reproduce these surfaces with palladium and we dip it into gold solution, what we saw is that there was more gold at the edges than on the other parts of the palladium structure. How am I doing for time? Okay. Again, another application we looked at is to see if we can make regenerable sensors. Okay, and regenerable sensors need some kind of control over. For example, we're doing SIRS-based regenerable sensors here, so we want to look at the photocatalytic activity as well as the SIRS activity at the same time, and try to balance the two. And we try to do that with the amount of SIRS active metals, so silver in this case, and our photocatalytic material was titanium, and so we made titanium-based colloidal structures and deposited silver on it through electrolysis deposition, and you can see the reaction there. So we deposited the seed layer using tin and palladium, and then we used the silver mirror solution to deposit our silver particles at different times, keeping concentration of the silver constant, and then at different silver concentrations, keeping the time of reaction or deposition constant. And the reason we're doing this is to find a balance between SIRS response and photocatalytic activity. So once we find our optimum condition where the SIRS and the photocatalytic activity balance each other, we did photocatalysis of the rhodamine B on the surface, and we showed that we could reuse the sensor over and over again on the right side. But more importantly, if you look at the bottom right hand side, what we show is that you could use these reproducible surfaces to get repeatability on different parts of your sensor surface. For a Raman, for a SIRS substrate to be able to do this is quite great if you're into that area, to be able to get the same SIRS response for the same concentration on different areas of your SIRS substrate. And the added value of being able to reproduce those surfaces is, again, another advantage. So then we thought, okay, we can make photoactive materials and get them reproducible at the same time. Can we use this combination to tackle the big sensing challenge on hydrogen that everyone's working on? So what we did was we got our resistive IDTs, deposited our polystyrene template on it. We etched it as we've been doing, deposit titanium on our surface, heat the titanium up to make it crystalline. So that because the polystyrene escapes the titanium, the polystyrene escapes the structure. So what you're left with is a shell structure of titanium colloids. Okay, so these colloids are all shell. It's empty on the inside. And then what we did was we add palladium on the surface. So we decorated with palladium. And the reason we do that is because titanium is not active for hydrogen sensing if you want to do room temperature hydrogen sensing at low concentrations. So we put palladium because palladium is active in absorbing hydrogen, but also it works as a catalyst to convert hydrogen to water. And we were hoping for the titanium and palladium to work synergistically to enable us to detect low concentration of hydrogen at room temperature. And it did exactly that. So we actually operated this sensor as an amperometric sensor. We operated at 9 volts, including light activation. And what we saw is that at 33 degrees, we were able to detect down to 60 ppm of hydrogen. All the way, the data is not shown here, but we've done all the way up to 80% of hydrogen detection with the same sensor. And the selectivity as well we have tested, and we could see NO is one of the main contaminants with commercial hydrogen sensors, and it went well against NO, and it's very selective towards hydrogen. So repeatability was also gave us very good results. We published this and we patented this, and we saw that we got a lot of response from aerospace community. We got actually contacted by Safran from France. We got contacted by contractors from NASA, and they actually asked for some of these sensors to be sent to them for testing, which is what's happening at the moment. There's some transducers that we've sent in US, and the main part for them was the materials that we've used and the reproducibility of the materials as well. So that actually helped us greatly with this approach that we had taken. Repeatability of the sensors I'm showing there is more than 99%. It was really nice, repeatable sensors. One of the last work that I'm presenting, okay, so we thought, now we have titanium, can we make titanium gold urchin-like structures for regenerable sensors? Again, we wanted to tackle the reproducibility when we talk about SIRS substrates. Okay, so what we did in this case, we have our polystyrene deposited, we etch it, the second step, or oxygen etching. We deposit our titanium on the surface, and then what we calcine it. So again, as I mentioned before, once you calcine it, the polystyrene escapes the structure and you get this hollow spheres, and then we deposit our gold as we've done before on polystyrene. So now we know that once we deposit electrodeposit spikes on it, we get this nice urchin-like structures. But what we're trying to do here is also control the spacing between the urchins, as well as having the added advantage of the photoactive urchins. So these are the SCM of the real structures, and as you can see, the structure doesn't change all the way to D, where we do sintering. In panel E, we now deposited gold on it. We're at that stage. And panel F, we've deposited spikes, gold spikes. As you can imagine, we've electrodeposited this. So it was interesting to see that the electrodeposition only occurred on the tip of the colloids and not on the surface at the base. So why was this happening? We came to Chris Harrison, who's there, and said, can you model this for us, the electrical field, and tell us why this is actually happening? So we compared simulation between a thin film, which you see on the left top area. Okay, we're looking at electric field and also the voltage, and we see that once you go into a colloidal structure, your electrical field is actually concentrated on the tip of these colloids. So that's why when you do electrodeposition with a constant voltage, you get your...
We're running short of time. We might need to wrap up.
Okay, okay, one more minute, I think we'll be done.
No, all good.
Okay, so so that's why the spikes come and deposit on the tip as we desire. And what we ended up with is, of course, these urchin structures with titanium underneath, gold on the surface, and hollow in the middle to give us that extra surface area. So we use these for SIRS again. And what we saw is that the higher the electrodeposition time of the spikes, of course, we get increase in SIRS response. We found our optimum conditions there, and we use it for regenerable SIRS. So on the right side, what you see is the cleanup of the surface when you expose it to UV, and we monitor that with the SIRS response. We've done simulation FDTD on this, and we see that when you deposit spikes, and because of the nodes, you get enhanced SIRS or hotspots on the surface. Of course, in our model, we just put these triangles, but the real spikes don't just have one tip. Every part of it is like a node or active area for SIRS enhancement. This is the last slide, so I'd like to thank all my collaborators, of course, Ahmed and Sam, involved in all of these works. I'd like to acknowledge all my colleagues, the PhD students that have worked on this, the technical staff, and the funding bodies, of course. So I thank you all for your time and attention.